begin with the, so I'm going to take you through, the problem we're trying to solve and then how we go about trying to do it. So let's see, I'm going to share screen and then go full screen, and I think that should work. Okay. I can see many of you, not all of you, but do let me know if you don't see the screen that I see, which is a slide which says hunt for the red cyano, story of using a ship deployed UAVs to look for trichodesmium blooms in the South Pacific. Everybody sees that? Okay.
That's good.
Good. First, I will get the acknowledgements out of the way. This is a project that I worked on with several of my colleagues. My friend Chris Zappa was the PI, and it is funded by the Schmidt Ocean Institute, and lots of people on the ship to thank. So we've gotten that out of the way. The most important thing I want to do is I want to thank Alex Engel, who was a professional photographer and blogger who was on the ship, who took most of the videos and photographs that I'm showing you in this series. And I'm going to put in the chat box after I finish talking a link to the cruise. I'm going to do it after I finish talking so you're not distracted when I am talking. A link to the cruise website where you can actually go and see the longer videos and the other information that Alex collected about the cruise. So now we play the virtual music of Mission Impossible. And so we got this instruction. Our mission, if we should accept it, was to go find the red cyanos that rule the South Pacific, right? So that's basically our mission. Scientifically speaking, we were trying to find trichodesmium. Our interest in trying to find trichodesmium was to develop new ways to remote sense this organism and to understand how surface blooms of this organism changes the air-sea flux of material and energy. What I mean by that is that if you had a surface bloom, then how does it change how much gases are basically being transported across the air-sea interface? How much heat is being transported across the air-sea interface? So that was basically our question, to find new ways to find tricho and to find out how surface blooms impact air-sea interaction, okay? So now I'm going to stop share and reshare this next video, which is, what is it, right there? Okay, and I'm going to go full screen on this, full screen, right? And then hit play. And now you should hopefully hear the sound as well.
Ready? Okay, VTOLs are ready for ascension. Okay, here we go. Launching in 3, 2, 1. Launch now.
We're here on the research vessel Falcor again. We were here in the fall of 2016 off the coast of Darwin, Australia. We're back again on the Falcor, this time north of Fiji, studying trichodesmium.
Trichodesmium is a really interesting beast organism. I've been studying it for a very long time. These blooms can be massive. We see them from satellites. They can cover 200,000 square kilometers. And the big question is whether a bloom of this kind changes the exchange of gas and energy through the air-water interface. Because these blooms are fairly large, they could have a widespread effect.
It's really a hugely ambitious project.
And this expedition is the first time that there has been a VTOL, vertical takeoff and landing, fixed wing, totally autonomous takeoff on a moving vessel.
In this particular cruise, we've been using sea surface temperature as one of the criteria for trying to find where trichodesmium might be. So we've been analyzing daily maps of sea surface temperature and guiding the ship based on where we see those warm waters.
Rich, this is Amber. Let's set a transect course for the front. Over.
What we're doing is trying to transect the front, the change in the temperature. We have this course plotted out, which is basically a zigzag. It sort of looks to me like a sewing machine line. What we're looking to do is mark down the position where we cross that front. So we're going from either the colder to the warmer water or warmer to cold. The really interesting thing about now looking for a specific temperature is we don't know, are we going to get that 0.3 of a degree change in 5 minutes or half an hour? Are we going to find that 0.3 of a degree temperature change at all? So that's something that I've certainly never done on board Valpro before.
Fronts have been studied from ships. These are really interesting and important features for us to understand. The fronts are very dynamic, and we need to be able to both see them at scales ranging from centimeters to tens of kilometers at the same time, synoptically as we call it. And that's difficult to do from conventional shipboard studies. The reason I'm really excited about this is because the drones allow us to do that.
Any sort of feature on the ocean that changes quickly over small horizontal distances, those present a challenge for modeling. So it's really a magnificent step forward in engineering that's helping us to do science that's very agile, tasking of the UAVs, being able to see data come down from the UAVs and make the determination to change the flight plan mid-flight. That is really an awesome development.
On the ship and floating around the ship, we're able to capture that data as well. You would have never known that patch was just 10 miles away and a valuable scientific target.
Thanks to our ability to act dynamically using real-time data, we tracked down pumice, which was likely to be the remnants of an underwater eruption near Tonga in August of 2019. The data we collect at times like this, such as thermal imaging and hyperspectral color imagery shown here, allows us to understand the effect of surface material, in this case the pumice, on sea surface temperature.
Aloha, my name is Kelly Mariko Anoyokopu'uvai-Lewis. I'm a PhD student at the University of Massachusetts, Boston, and I'm a satellite oceanographer. And there's a series of problems involved with satellite oceanography, one of them being there's a fair amount of clouds on our planet. 2, scaling. A lot of these satellite imagery come at a kilometer scale, or they do scale down to 30 meters, but then they don't, you don't get to actually get them on a daily basis anymore. So one of the really exciting things about being on this cruise is that we can use ARM instruments that validate ocean color satellites, and the UAVs can fly at varying heights above clouds, below clouds, and we can basically start to bridge the gaps between what we're seeing on the water all the way back up the satellite.
Okay, so that was a quick attempt at taking you on the ship with us, and you met many of the people that I lived on board with for almost 45 days. The last person that was speaking was Kelly, a PhD student that was working with me on the cruise, and she was doing a lot of the optical work. But to continue on with the story, let me stop there for a second. Questions? Any questions? Okay, let me ask you a question. Show of hands, and you can just lift your hand up or use the raise hand function in your participant thing. How many people want to go on a ship and do something like this? Do you really want to be away from everybody that you know for 45 days? Well, if you did, that's probably the best ship to be on. It's run by a private foundation, and they do not hold back on the food. Actually, the 2 chefs on board, they have 2 chefs, both worked on private yachts, and they do not stint on trying to feed you. I probably gained about, 8-9 kilos when I was on that ship, even though I was working really hard. But fun and games aside, we were there to do science, right? So onward with the next set of slides. And let me see, let me go back to full screen. And at this point, because it's full screen, I can't see you. So I would like you to unmute yourself and ask questions when you do, please. And just jump in and ask questions. Don't hold back. So first thing is, what is this thing called trichotillomania anyways, right? When we talk about the red cyano, I think that came from the Red October thing. I'm not sure where I got inspired by that. But anyways, the fact is trichotillomania is a cyanobacteria. So it's also known as sea sawdust. One of the stories that we've been told was that Captain Cook, in his voyages, when he was off the Great Barrier Reef, his crew often thought they were going to run aground because they saw this thing in front of them, which they thought were coral reefs, while actually they were dense, dense blooms of trichodesmium. But sailors, because it looks like sawdust in the sea, in the water, sailors call it sea sawdust. It is a cyanobacteria. It is an autotrophic cyanobacteria. It's a prokaryote. It used to be called blue-green. Okay, this is basic for you guys. I'm not going to go there. It is ancient, as I think you probably all know. It's been around for a very long time. It fixes carbon, autotrophic, I said. It also fixes nitrogen. And I think all of you are probably very familiar with its kissing cousin that happens off your shores right there. And we'll be seeing a lot of pictures of that as well. We say that it is responsible for carbon sequestration because it fixes nitrogen. It brings in new nitrogen into the surface oceans. And when these blooms die and they sink, they take down carbon with them. Or when the nitrogen that they introduce into the environment is used up by either other phytoplankton that sink, they take down the carbon with them. So either which ways, we basically ascribe the carbon fixed or the nitrogen fixed and then the subsequent carbon fixed to carbon sequestration. And for me, it's an enigma. It's a mysterious beast that I've been studying for almost 30 years now, and I can't say that I know much more about it than when we started. It is very common in tropical waters. And here's a map that basically shows some of the places where trichodesmium is seen. And you can see that, we basically paint most of the tropical oceans in that teal color, the blue, sort of bluish green color, where we think there's tricho. Now, they're not there everywhere, but they could be anywhere in any of those locations. We had been here once before to this area around Fiji back in 1998. And we had seen trichodesmium in these waters. So one of the reasons I had selected Fiji as our operating area was because we were reasonably certain that we will find blooms when we went there. Now, we had requested the ship in January, February, which is when the highest likelihood of calm weather was going to be, but we got the ship in November. So, you basically got to go when you get the ship. So that's basically what happened. But we went there because we know that we can find trichodesmium in these waters. I think I'll leave it at that. I might come back to this slide later. So what does it look like? Again, I think you might have seen pictures, but I'll just quickly walk you through a whole bunch of these slides. So this is what it looks like under a microscope. What you're looking at are colonies of trichodesmium. Colonies made up of individual trichomes that gather together. And the trichosphere, as we call it, is actually an environment that also hosts a whole bunch of other bacteria and other organisms. So that's basically what a trichodesmium looks under a low power microscope. We can look at it a little closer. You can see the individual trichomes in this picture. If you can see my mouse, like that is an individual trichome. So each colony we estimate has maybe about 20,000 cells. That's what it looks like when you catch it in a bucket. So, we basically pull back and you basically throw a bucket over the side and you might find something like that. And this is not trichodesmium, but actually, I'm going to sort of, I don't know, it's difficult to ask these questions when we're doing Zoom, so I'm maybe not going to do that. But just to tell you, this is a photograph from the Baltic. So anyone who wants to unmute themselves and tell me what they think this is? Yeah. So I did a cruise in 1999 with Suze Kratze, and this is a photograph I took when we were on that. It was taken through a porthole, and this is just to give you a sense of the size, because these are much, much bigger than the trichodesmium colonies we normally find. These are the colonies here are in the order of a few centimeters, whereas trichodesmium is maybe a centimeter at the maximum, but quite a bit less than that. And this again is in the Baltic. This is from the side of a small boat, and this is just to sort of there are a couple of things I want you to get out of this particular picture and the next picture that's coming up. One is you can see this is almost like when you throw lawn. When you mow the lawn and you throw the clippings into the water, that's what it looks like. So we saw these blooms where these basically are just on the surface like that. But as you saw in the previous photograph, they're not just at the surface, they're also distributed in the upper water column. Because that porthole is probably about 1 meter below the surface, and we could see there's quite a lot of colonies in the through the porthole. That pen there is just to give a sense of scale. But one other thing I would like you to get out of this is that you can see the sky. And I don't know if you know if you understand what I mean by that, but if you look in these parts, like right around here, you can see that the sky is being reflected on the surface. And you're seeing that the sorry, here in this case, the cyanobacteria is not popping through. In other words, what this is to show is that while the pen is floating on the surface, a lot of the colonies you're seeing here are just below the surface. They are not above the surface. And that's an important feature we need to know for remote sensing. Here's a photograph that we took on this last cruise of a trichodesmium patch from the side of the ship. And here again, you can see the sky. So you can see that the tricho is just below the surface. And what you can also see is this thing here. It's a it's a rock, and I will talk more about it later. But you can see that that is actually above the surface. It has basically broken through, and you can see like the wake where it is moving at a different speed than the tricho slick. So you can actually see a wake that is cutting through the slick that way. The point of this is to basically again say that the things that are on the surface are going to be moved around by the winds very differently than the things that are in the water. I think that should make sense to you. If it doesn't, please stop me and ask me what I mean by that. But this is mostly to show that, and just to show again that there's sky reflectance, and what you're seeing is mostly below the surface. Then this is again from this last cruise. You can see how patchy this can get. So when you're looking at it, something from a height of about 2 meters, you're basically seeing this patchiness of trichodesmium, very dense in some places, and then you just have blue water in between, which you can then imagine sets up a real challenge. And so this is the same thing from the Baltic. So this is the boat that we were working in the Baltic. And so you can again see the patchiness and how it accumulates in these lines, depending on the direction of the wind and other things in the water. You can imagine how difficult it is to sample something like this. If you were to use conventional sampling tools, such as a CTD rosette that you see here, which is probably in the order of about 2 meters or 1.5 meters in diameter, with a series of individual bottles that we open and close to capture water from different depths. When you're trying to catch something that is at the surface like this, it is going to be very difficult. The very presence of the ship moves these things around. And so sampling this is very difficult, which is why we use something like this, a small boat that you see here, or you'll see another photograph of the kinds of boats that we used when we were on this cruise here. I would also like you to take a second, only a second maybe, to appreciate the blueness of the water. I have never seen water this blue ever in my life. Absolutely clear, except for the tricho. This is from the Baltic. This is from the Swedish Coast Guard. And this is a photograph of these blooms. And you can actually see the ship going, and you can see the wake of the ship. So this is very similar to the picture that I showed you before of the pumice cutting through the tricho, except now you're looking at it at a way bigger scale. And you can still see how when you have these floating blooms, you can see the wake and things accumulating along the wake. And also, I do not know, I didn't point it out to you, but you can see the numbers here is increasing. So we went from a microscope to a bucket to, so we are talking about millimeters to 0.5 meter to side of the ship, which is a couple of meters. And now we are looking at it from maybe about 2,000 meters. You saw it from the top of the mast, which is about 10 meters. Now you're looking at it from about 2,000 meters. And then here you're seeing this from a drone. And again, this is from the last cruise, and you can see how the trichodesmium is accumulating along these frontal features. And there is the small boat that we use to sample the trichodesmium bloom. And then we're back in the Baltic, back in your neighborhood, showing just a satellite image of the cyanobacteria blooms in the Baltic. And this is a space shuttle photograph of a bloom of trichodesmium of the Great Barrier Reef near Australia. And then, so again, we're going up in altitude. So now you're looking at something from about 200 kilometers from the surface, right? And then you can go even further up. This is again from a space shuttle photograph, and you can see here how trichodesmium is accumulating in these features that you see here. The one other thing I want you to take home from this particular picture is the clouds. So these are not trichodesmium blooms, these are clouds. Clearly, you can see the clouds over land, including the cloud shadow over here. And what I want you to see is that if you were just to look at it, it could be very challenging to distinguish clouds from these blooms at the surface. And it certainly is very challenging for satellites to do that very accurately. That's basically, again, it's a different scene altogether. It's taken from a satellite. That was from the space shuttle. This is taken from a satellite. And even from a satellite, you can see how wakes are formed when you have a ship or something like that that went through. So you can see that there. And all these blooms of trichotesmium here, and some individual boats that are anchored off here. This is from a Landsat. And so you're looking at something that is about a 30-meter resolution here. And so this whole thing with clouds, I just want to get it out of the way, so we won't come back to it. But if you take an image like this and process it in a normal way to look for a satellite image, you would get something that looks like this. And as you can see, there are no clouds in this image. Yet, if you looked at the satellite processed image, you'll find all of these as masked as clouds. And the reason for that is because in most satellite processing, very high reflectance that you see in the blooms that you see here get misidentified as clouds. And so you often end up thinking there are no blooms and it's all cloudy, when actually what you're looking at is the bloom itself. The other thing I want you to note in this particular slide is the difference between this and this. So this is the normal satellites we use for ocean remote sensing, and it has a 1 kilometer resolution. And you can see that none of these features are actually coming through. It just gets too blocky. So the take-home message, I don't know, number 2 or 3, I can't remember, I'm not keeping track anymore, is that resolution matters. You will see the blooms. I mean, now, like I said, you went from the microscope all the way to the satellite. And the fact is that the further you get away from it, the more details you miss. And so when you are looking at a 1 kilometer pixel image, it is going to be very difficult to actually map that to to study blooms with something like that. The other take-home message from the series of slides you've seen thus far is sampling is really tricky. If you go back to the patchiness slide that I showed you, so if you're looking at something like this, are you going to take water from this spot here, or are you going to take water from this spot here? And what do you compare, either from this spot or this spot? How do you compare that to what you see from a satellite, which is at best 10 square meters? At worst, it's a kilometer. And I have no idea how you're going to compare a point to the kilometer, but how do you compare something like this even at 10 square meters? Challenges. And, yeah, that's what makes life interesting. So having gone through this, now I think Suze went through some of these topics with you, so I'm not going to spend any time on this, except to say that the way we do remote sensing is using the spectra of absorption. And so this is basically absorption spectrum for trichotesmium. It has unique pigments in it that we can use, that gives it an absorption spectrum. So it has phycoerythrin, which is a phycobilly protein that is found in cyanobacteria, that has an absorption peak at around 495 nanometers, another absorption peak around 550 nanometers. And we can use these spectral features to try and identify trichotesmium. If you were to take those spectral features and stick them into an optical model, something like perhaps what Susan might have talked to you about, you can calculate a reflectance. You can imagine reflectance as almost like what your eye would see, right? So if you basically think of this color bar that you see here at the bottom, then a reflectance that is high in the lower wavelengths, so between 400 and 500 nanometers, like you'd see with this line here, basically would make the water blue because it has the highest reflectance in the blue wavelengths. And that corresponds to seawater with nothing in it. So these are the really blue open ocean waters that I showed you in a picture, and I'll show you again later. If, on the other hand, you are looking at a reflectance spectrum that has a peak around here, then you're going to see that peaking in the sort of almost yellow brownish region, right about there. And that's basically what trichotesmium looks like. And this basically means that there's no blue, there's no red, and what you're looking at is a sort of leftover of a green-yellow color, and that's essentially what the bloom of trichotesmium would look like if you were to see it from above, right? And I just for other, just as a point of comparison, I've plotted some of the other phytoplankton in the optical that we can run through in the optical model. Another point of comparison is blooms of coccolithophores. I don't know if you have seen pictures of blooms of coccolithophores, but sorry, this rings. I'm gonna, okay. These blooms of coccolithophores have a bluish color, milky blue color, and that's essentially how it comes out in the optical model. So that's sort of the background. That's basically the techniques that we use to hunt for trichodesmium in remote sensing. Questions?
Yes, I have a question. So you were talking about trichodesmium's unique pigments, and I was wondering if how does that change its ecology compared to like other cyanobacteria, like where it lives and how deep can it live and all that.
Aha. Thank you, Eric. That was the topic of my PhD thesis.
All right.
So let me ask you, do you have a sense for, I mean, this is not to pick on you, please do not feel that way, and don't worry about it if you don't, if it's difficult, but do you have a sense for how light is transmitted in the water column?
Yes.
In other words, can you tell which light penetrates the deepest?
The blue.
Okay. Is that true in the Baltic? That's a trick question.
I don't think so. I mean, only the thing with the Baltic I can think about is that it's much more organic carbon and particles in the water, which make light don't penetrate as deep in.
Sure, but the color.
The colors. I can't just answer that.
Okay, so
I think it's blue still.
That's because of other particles, right?
Andreas, yes?
That's because of other particles that discolor the water in the Baltic Sea. I mean, it's hardly blue.
It is not blue. This is true. The color of the water is not blue. That's what I meant to say. Particles have a role, but in the Baltic, what's really changing the color a lot is the dissolved matter. So it's the dissolved organic carbon that is changing the color of the water in the Baltic. And dissolved organic carbon has a very high absorption in the blue. So for example, if you looked at the absorption spectrum of dissolved organic carbon, it would look like this. Very high in the blue and almost nothing in the red and green. And what that means is that the blue light is absorbed. And so when you look at Baltic water, it has got a slightly more greenish color, and it is darker for sure, right?
All right, I misunderstand the question. I thought, okay, yeah.
Right, but going back to what you're asking Eric, so what does that do to the pigments and how does that change the ecology of the cyanobacteria? Really interesting, right? So if you looked at freshwater cyanobacteria, for example, because the Baltic is, for me, hopefully I'm not insulting anyone, it's a big lake, right? But leaving whether it's a big lake or not, it's high CDOM waters, very high dissolved organic carbon waters. It's like a lake in that sense, because many lakes are the same way. Not all lakes. Many lakes have also this high dissolved organic carbon problem, or dissolved organic property. And what that means is that cyanobacteria that live there have to adapt their pigments in a way to absorb light that they have available. You know, you got to basically use the light you have, not the light you want. That's basically what somebody told cyanobacteria when they were born. So what they did was to change their pigment composition. And this is essentially why you have cyanobacteria that have a lot of phycobility proteins and have a lot of phycocyanin. Freshwater cyanobacteria, for example, have a lot of phycocyanin that has a high absorption, that has absorption in the 600 to 650 nanometer range. And what that means is that they're able to use light that is greener, right? And that's essentially what is happening in the Baltic or in a lake, which is that you're changing your absorption spectrum to fit where you are and to use the light that is available to you. Does that make sense? So your question is really good, because the question here is, how is tricho doing this? And the point is that trichodesmium has this absorption spectrum around 495 nanometers, because that is the blue light that is available in the open ocean conditions where it's often found. Whereas if you looked at a freshwater cyanobacteria, it will have a completely different absorption spectrum, because it is using the light that is found where it is, which is very likely to be much greener, because your blue light is absorbed by CETO. Make sense? And does that get to what you're asking, Eric? So yes. Now just to pick on that point just one tiny bit more, the opposite of that is, how does that affect the light underneath? So this is one of the things we are trying to do in this project, right? We are trying to say, if you have this bloom of trichodesmium at the surface that is absorbing all this light, then what is the light field underneath the trichodesmium bloom? And that is the point we were trying to get at. So how is that light field underneath the trichodesmium bloom changing? How is it changing the heating of the water? Is the absorption so the sunlight is coming in, it's hitting the trichodesmium blooms at the surface, it's absorbing heat along with the light. And that's heating the surface. Is that then cooling the water underneath it? Because if the bloom wasn't there, sunlight would have penetrated deeper and it would have warmed the water deeper. By now blocking the sunlight at the surface, are you now cooling the water deeper and warming the water on top? And how does that affect all of the heat exchange with the air and ocean and all the rest of that? So those are all very relevant to the question you're asking.
I'm sorry. Shouldn't that affect like algae and other growth at the bottom as well?
Indeed, indeed. And that phenomenon is called self-shading. And it is actually a competitive strategy followed by cyanobacteria in freshwater. In the open ocean, there's a lot of mixing, and so it is slightly less important because, yes, you do have blooms, but the whole idea of self-shading in the open ocean is not as critical because of wind and things like that. You have a little bit more mixing. But in freshwater systems, self-shading is a competitive strategy. And those phytoplankton that actually can float to the surface and get light are going to be shutting out the light for those underneath them. So that is indeed an absolutely excellent question.
Ajit,
Yeah.
it seems like, wouldn't you just be putting like the lid on a pot of water so you would seal in the heat?
Yes and no. In this case, it is like a lid on a pot of water, except the heat is on top, not underneath. Make sense?
Yeah, but I would think the bloom forms, there's a collection of heat and then it's capped off.
Right. No, so the collection of heat is along in the thin layer where the bloom is. And the question is what happens underneath the bloom, right? And then, of course, as you can remember, Rachel, quite well from our cruises, you have also this diurnal mixing that happens, right? We always find blooms that are basically the wind fields change during the course of the day, and the blooms form. I mean, for us on this cruise, it was frustrating because the blooms will always form around dusk when we cannot study it with the drone, or when we can't do optical remote sensing. They'll start forming around 4 o'clock in the afternoon, and it's at that point almost too late to measure light.
Excuse me, I have a question too with this graph. Go back one.
Oh, sorry.
Maybe. No, front one with the absorption rate here.
Yeah.
So I was thinking the trichodesmium, for example. How can you distinguish those that peak from the combined effect of all the others at the same wavelength?
Good question. So we have two things. One is the magnitude. So in other words, trichodesmium is just brighter, or it is more reflective than other phytoplankton, right? And so, the way you want to think about this is for a given volume of water for a given chlorophyll concentration. That's basically how the optical model works. So for the same concentration of chlorophyll, trichodesmium is just much brighter than other phytoplankton. Right? Other phytoplankton absorb a lot, and why? Okay, no, stop, Ajit. You're getting ahead of yourself. Question back to you, Leo. Why do you think, it's an unfair question, but I'll just throw it at you anyways. Why do you think trichodesmium is brighter? And I'll give you a hint. Think champagne.
I was going to more oxygen.
Kind of, but not really. Think champagne again. What do you have in champagne?
CO2. Bubbles.
Bubbles, exactly. Yes. And a lot of the cyanobacteria have gas vacuoles in them, which are basically gas bubbles. And why does champagne sparkle? You're seeing an increased backscatter because you're seeing a change in refractive index. In other words, because it has gas, right? You're going from liquid to air when light is shining on it. And so you have a change in refractive index. And when you have a change in refractive index, you're changing the backscattering property. And that's basically what makes champagne bubbles sparkle. And my favorite organism, trichodesmium, also sparkles that way. So it has just a higher, brighter reflectance signature. And so one of the primary ways in which we look for things like trichodesmium is the backscatter. And then, yes, indeed, there are some similarities in color. For example, you'll see that other phytoplankton, what I call average phytoplankton, also have that green peak. But you can also see there's a subtle difference between where the average phytoplankton peaks and where trichodesmium peaks. It's shifted a little bit. But these are great questions because we cannot distinguish these subtle differences in the satellites we have today. we are all waiting for what we call hyperspectral satellites. Hyperspectral being that you have not 5 bands or 7 bands or 14 bands, but 256 bands, where we can really make you can distinguish spectrally these changes, which you cannot see otherwise, right? So now thank you for the question, Leo, because now you tripped me into the next issue of resolution. We talked about spatial resolution. In this case, now we're talking about spectral resolution. To find trichodesmium, we need high spectral resolution in addition to the high spatial resolution. Make sense? Yeah? Okay, moving right along. I just want to very quickly talk about the technology that we used. So the drone that you saw, incidentally, I'm a little bit of a snob about this, so I will just confess to that. I'm a snob. I don't like to call them drones. I call them UAVs, unoccupied aerial vehicles. And that's the way it is. But anyways, I will slip out the word drone when I'm not thinking about it. These are hybrid. What that means is that they can take off and land vertically. They don't need a runway. But once they have gotten to a particular height, then they're pushed forward with a propeller. And the distinction between these and the popular drones, and I will call them drones that you get in a toy shop, is exactly that. Most of the drones you get in a toy shop are quadcopters or octocopters. They're basically variants of a helicopter. They have propellers on top that basically take them up and down, and then they move forward or backwards. But they don't have propellers that push them, right? The propellers give them the lift, and then they move. These are hybrid. So they have propellers that lift them, and then they have another propeller that pushes them. And that's why we can use these from a ship. That basically also gives them speed and endurance. So these have electrical motors for takeoff and landing, and have a gasoline motor that basically gives it the forward motion. What we had on this system was a fully autonomous flying system, which basically means you basically program it in the computer, and there's no human pilot involved in active changing of anything. If you want to change the flight pattern, we just go move a point on a map and move it to a different place, and it will then steer the UAV to the place where we want it to go. It goes at about 45 knots, 23 meters per second, which basically is a lot faster than you can get with an octocopter, and that's the big advantage. Because it goes at 45 knots, you can cover a lot of territory with it. This particular UAV that we're using weighs about 52 kilos. It has a wingspan of about 5 meters, a little less than 5 meters. And the other big challenge with these UAVs is how much weight they can carry. And the fact that this can carry almost 7 kilos makes it very suitable for putting science payloads. Most of the drones that you get in a hobby shop have a camera on them. Cameras are great. They can give you, a lot of the videos that you see that you saw there are coming from a camera, but you cannot do quantitative science with them. You cannot get reflectance spectra to go about resolving trichodesmium without a radiometer of some sort. And as you'll see, what we also did was we built these flexible nose cones. So when we were flying missions almost continuously, and each nose cone had its own payload. One was measuring hyperspectral visible wavelengths. One was measuring infrared heat. One was measuring turbulence in the atmosphere. It basically had a meteorological package that was measuring atmospheric properties. So we could take the nose cone off, put a new nose cone on, almost like you'd have in a racing car. So the drone would land, we basically take off the old nose cone, put in a new nose cone, change out the batteries, and it can take off again. So the idea that it had swappable payloads was a very big deal. And it had an endurance of almost 12 hours. Again, if you compare them to your hobby drones that you can get, if they fly for 20 minutes or half an hour, you're happy. We could fly these for 12 hours, which means we can again cover a large territory. The fantasy that we were trying to live here was the fact that you actually had eyeballs on the horizon. You could see 200 miles in front of you what you are going to, and you can use it to hunt around the ship to find features that you could not see from the ship. So another terminology I'd like to throw out there is that these are the 21st century crow's nest. Does the term crow's nest sort of make sense? That's the thing that they had on top of sailing ships where someone would be keeping an eye to see what's out there. This is our 21st century crow's nest. We could fly these from the ship and basically look 200 miles around the ship as to what features we want to look for. And we were getting a real-time feed of the data. It's not all of the data because we are still stuck with bandwidth issues, but we could actually get some of the data, including video feeds back, so we could visually see what we were looking for. this is our cruise. This is Fiji here. We left out of Suva and basically made this pattern. Why this pattern? You know, this is kind of strange. You know, what kind of a funny shape is that? So now the question is, how do you find tricho? How do you find cyanobacteria? We know, so, you know, it's like, okay, a couple of pictures, pretty pictures. So this is us leaving Suva Harbor and, you know, from the ship. And so then the question is, how does one go about finding tricho? We know two things about tricho. Well, we know a few things about tricho. So the most important thing that I would like to use first is the fact that it likes to be in warm waters. So we can get real-time satellite images every day on the ship of the region. So here you're seeing a map of sea surface temperature. There is Suva right there. And you could see that the warm waters were to the north of Suva, the cold waters to the south of Suva. So we wanted to be north of Suva. We also know that tricho likes it to be calm. For the blooms to happen, we need flat, calm surfaces, right? So when we use a website like Windy, that basically gives us wind speeds. These are forecasts of wind speeds. So we can actually look to see what the wind speed is. And what you can see here is that, yeah, right around Suva, it's calm. But when you go north, yeah, well, sure, I'm pointing with my finger, so you can't see my finger. When you go around here, you're seeing wind speeds that are going up to 15 to 20 knots. There is no way you're going to find surface blooms when the wind speed is 15 to 20 knots. Actually, once the wind speeds go past 25 knots, we can't even launch the UAVs. So we cannot work in high wind waters, right? So it is nice and warm out here, but it's also windy. However, Windy, the website, not Windy, the phenomenon, tells us what it's going to be in a couple of days. So we can see that, okay, today this is on the 2nd of December, it's windy. But if you go a little further ahead, on the 1st of December, it's windy. If you go a little further ahead, it's calm. So we can use real-time forecasts of this kind to say, okay, we can be there in a couple of days, it's going to calm down and maybe it'll settle down. So we were using real-time feed of sea surface temperature and wind speeds to tell us where we want to go. And that's basically why you had the ship doing that strange thing. We were trying to stay out of the high wind areas and at the same time stay within the high temperature areas. However, one other thing about trichodesmium that we have figured out, and I have some hypotheses, I'm not going to speculate to this class right now, I'm happy to answer questions, is that it also likes a few other things. It needs a calm, it needs the sun, it needs nutrition. And we have some ideas as to where that nutrition is coming from. So we know that if we went too far north, we're not going to find it. It's almost like a game, right? Further constraining our choices as to where we go is permissions of countries that we can work in. So we had permission to work in Fiji, we had permission to work in Tonga, but we did not have, when we had permission to, so there's a rock out there which France claims, and so half of the South Pacific is French. And there I said it. I clearly can see how I feel about that. So we had French permission, but we did not have permission from some of the other islands. And therefore we could not just go wherever we wanted because we had to also stay out of territorial waters of islands. And even if it is just a rock, you can claim 200 miles off the rock. So basically you get a huge patch of the ocean that you claim because there's a rock out there. So there were some places where we could not go. And so these are the things that constrained us to where we could go. So I was using real-time satellite images, wind speed forecasts, and the sense that we had to be somewhere around the islands to figure out where we wanted to go. And when we went north, we found absolutely calm waters, the bluest I've ever seen in my life, but no tricho because we just went too far north of the islands. So we came back south, and that's basically how the cruise track had this funny look that it did. Details of the nose cones. So you can see these are 4 of the payloads that we use. So this is just the stripped down electronics. My colleagues, Chris Zappa and his team, a bunch of engineers, were basically putting these and repairing them, fixing them, because they always break. So that's basically what they did. And this is essentially how it works. So you basically see that's the UAV without the nose cone in place. And that's basically what it plugs into. So you can see him, Scott, basically plugging in the nose cone. You tie it up and off it goes. A couple of things for you to see in these photographs is that prop here is the gasoline engine prop that pushes the plane forward. And these, I can barely see them, these black propellers that you can see in this or you can see it in this also a little bit. This is called feathered when they are completely lined up with the wing. So they are they have the most aerodynamic shape. They're feathered, but those are the props that help them take off vertically. And once they're off up in the air, we are in the control room and we are looking at the data that's coming back. And we are looking to see, what basically we can get visual feeds so we can see what's out there. We are also getting the radiometric measurements that are made. And this is basically what it looks like, the radiometric measurements. So you can see the blooms of tricho and the temperature, sea surface temperature. And a very quick aside, we went there to find tricho. But we found something else also, which was absolutely fascinating. And this is the portion of my story I say, welcome to the pumice land. So what is pumice? Where does it come from? What is it made of? Where does it go? So many questions, so little time. So pumice comes from a Latin word for foam. It is a very light, extremely porous igneous rock that forms during volcanic eruptions. When it's superheated, the rock is ejected and it basically very quickly cools and it depressurizes, basically filling it up with gas bubbles, which basically means that it floats. So this is floating rock. It is rock, but it floats on the surface. It's mostly made of aluminum silicate, but it has other interesting properties that we're looking into. It basically floats around till the porous cavities get filled with water at some point, and then it sinks. These are some photographs that I found on the internet of a volcanic eruption that happened about August, so about 2-3 months before we went out there. And you can see that this is ocean, right? This is off a sailing boat. And you can see it is completely covered with pumice. So that's basically what it looks like as they sail through this region. It is so much that, so this is Fiji, and the eruption happened there. And while we were hunting around for tricho, I was also really interested, because this is one of the hypotheses I was trying to test out. I was really interested in trying to find these pumice rafts. So basically, this was reported by a sailing yacht on the 9th of August, and we could see them in the satellite images. So you basically can see this is the pumice raft on the 9th of August. And of course, everything is Manhattan. That's where I'm from. So we basically say, well, they say it was bigger than Manhattan. Nothing is bigger than Manhattan, but that's what they claimed. And this is what it looks like in the satellite images. One of the interesting things you can see here is that these black or dark features here are cloud shadow. They're not holes in the pumice, but there's actually shadow from the cloud that you can see with these high resolution satellites. There was a lot of hype about this. They basically, it was floating towards the Great Barrier Reef. And one of the speculations was that, you can change the reflectance, and therefore you're increasing albedo. And so you're preventing the warming of the ocean. Hype, like I said, and much of it came from this particular image, where you can see the shape of the clouds is very much like the shape of the pumice raft underneath. So the question was, is the pumice raft causing the clouds? I mean, clearly the clouds are not causing the pumice raft, but is the pumice raft changing evaporation and things like that is actually causing that cloud formation to look the way it is? Coincidence, my friend, coincidence. We shall prove that at one of these days, but until then, it is just coincidence. It basically broke up, it drifted westward, and over the next month, we could track it in the satellite images till about the 9th of October, when you can see it accumulated along the shores of one of the atolls that is north of Fiji. So it basically came across, and you can think of it like a comb, right? When there are islands, it accumulates on the beaches. Where there's gaps, it goes through. And that's essentially what happened here. That's basically what it looks like after it passes the island. So you can see the atolls on this side here, and you can see how it is sort of even more broken up now, and you see them as streaks. This is on the 9th of October. We were there about a month and a half later. I wasn't sure that we'll actually see any, so this is just to show you the progression of the pumice as it went westward. I wasn't really sure if we'll see anything till we did. One day, I was standing out on the back deck and looked over the side, and I saw 2 of these, right? And it looks like, I thought they were actually little young coconuts, because that's what they looked like. Pulled it up with a net and looked at it, and it was pumice. So then we were able to use the UAVs to go find them. And incidentally, there was coconuts in the mix, just so you know. It wasn't all this thing, but this is basically what pumice looks like. Coconuts in the mix. Okay, I'm going to start. I mean, I know I'm running out of time, so I'm trying to go as fast as I can. But I do want you to think about those coconuts in the mix. What does that mean? What does that tell you about where the pumice came from, right? Think about that. Just a couple of pictures. There was also some bits of plastic, again, clues to where the pumice came from. And this is what it looks like in the UAV scientific payload. So you can see both in the hyperspectral data and in the IR data. And so we can see how the pumice is warmer than the waters around. So the pumice is absorbing heat while it's sitting at the surface in the sun. So that's basically what we can get out of that. Quickly round it up, 43 terabytes of data were collected. We flew 19,300 kilometers altogether during the 45 days we were out there, using the 3 UAVs that we had, 240 flight hours, 44 flights, 33 days, 9 scientists, 3 UAV operators, and a ship full of people. Really fun cruise, most fun I've had in a long time. That's all of us on the deck, the crew and the scientists. And thank you. Sorry, I ran a little late.